Good morning, everybody. First of all, thank you. I would like to thank the organizers for, particularly Muhammad, for inviting me to present at Oligo 2023. Thank you, Silva, for the kind introduction. Thank you for the organization. It's my seventh or sixth time at this fantastic conference. Always a great success. I'm really sorry for not being in person in Oxford, but traveling to and from France is quite challenging right now, especially today with all the strikes. But promise I will come back to Oxford at the later future edition of the Oligo series of conferences. So today, what I would like to do is give you a very short survey of what we try to do in the lab in Paris. And essentially, we focus on modified nucleoside triphosphates, and I'm pretty sure that Michael Hocek will give a very, very fantastic presentation later on this topic. What we do actually is we focus on two main projects. First of all, we try to use these modified nucleoside triphosphates to identify chemically modified aptamers. Obviously, we're by no means close to what uh, Nebosa and Larry are doing with fantastic somomers, but we try to expand the chemical diversity that is available in aptamer selections and try to improve the properties of aptamers. In a second, somewhat related project, well, because one has to synthesize these modified oligonucleotides, we try to develop approaches for the de novo synthesis of chemically modified oligonucleotides, focusing essentially on antisense oligonucleotides. So we'll exemplify these two research axes by recent projects, and I will start with the Celex using the modified nucleotides. So I think aptamers were introduced beautifully well by Nemboza and Larry and Ewan as well. So I don't have to dwell too much on this introduction part. So essentially what I try to do is to synthesize modified nucleotides, use them in Celex, and then identify modified aptamers for various applications. So there's actually different possibilities to do so. So instead of using canonical nucleotides and standard polymerases such as TAC under PCR conditions to then produce libraries, we first of all try to substitute one or multiple canonical nucleotides with base modified nucleotides with what we call exotic functional groups, which are essentially just functional groups that are totally alien to biology. In the second approach that was actually pioneered by Thomas Carell, we tried to expand the genetic alphabet using artificial metal base pairs and hence to introduce chemical diversity in aptamer selections. So focus essentially on the base modified nucleotide approach for the sake of time. So when I started my lab in Paris, we wanted to have one common synthetic precursor that we could then modify because obviously the synthesis and purification is not always that easy of these nucleoside triphosphates, and hence we could then form a subset library of chemically modified nucleotides who focused, fair enough, this may be not the best synthon on ethinyl EDUTP, but it's easy to make and commercially available. Then you produce that on larger quantities, synthesized a bunch of azides, and had this subset library of chemically modified nucleotides that we're currently using in aptamer selections to identify chemically modified aptamers. So we have already quite a few modified nucleotides, and we also have quite a few modified aptamers, but I will focus essentially on just one, which is a few years old now, 3 years actually. It's we identified the cubane as a sort of an interesting scaffold because it is a benzene bioisoster, and it does share actually a number of physicochemical properties with benzene, but obviously it's quite different as well, as you can imagine. It's not an aromatic, it's not planar. It does have an important ring strain, and because of this, the cubyl hydrogen atoms are quite acidic and can engage in CHO hydrogen bonding interactions. Also, cubane is quite an interesting scaffold in medicinal chemistry, where actually drugs and pesticides, the aryl groups of drugs and pesticides are replaced with cubane moieties, and the resulting cubyl analogs are usually either equally potent or more potent than the parent derivatives. So because of that, we thought that this would be an interesting scaffold to use in aptamer selection. So we synthesized the corresponding triphosphate, could show that it's compatible with enzymatic DNA synthesis under PEX and PCR reaction conditions. We then teamed up with Julian Tanner at the University of Hong Kong and focused on a selection experiment against the lactate dehydrogenase of PVVAX, which is an important biomarker for malaria. Besides being an important biomarker, it is also sort of a difficult target for aptamer selection, because there have been aptamers that have been raised against the PV LDH, but they're not capable of distinguishing the LDH from VVAX from the one from P falciparum, because they share a 90% sequence homology. So the idea here was to explore novel chemistry that deviates from flatland chemistry using these cubane modified nucleotides, and B, try to see if these modifications could trigger a specificity towards PVLDH and not recognize PFLDH. So after 15 rounds of selections, we identified a modified aptamer that does not have a super high binding affinity, especially when compared to isomers, but we achieved our goal because it is highly specific for PVLDH and does not really bind to PFLDH. We are even more lucky because we could resolve the crystal structure of the aptamer protein complex with a 2.5 angstrom resolution. And we'll just like highlight two structural key features. So as Nebosa showed yesterday, these cubane residues can actually, there's like 4 cubane residues that group together and form a hydrophobic cubane cluster. And that, in a sort of a lock and key type of mechanism, inserts into a hydrophobic pocket of the protein. And this is responsible for the interaction with the protein, as somomers do. Another feature is that we observed upon closer inspection of the crystal structure. There's a cubane moiety that is actually in close proximity to a carbonyl of an alanine moiety of the PVLDH protein. And actually, this cubane residues is within bond distance and forms adequate angles. And for us to believe that it engages in a CHO hydrogen bonding interaction. And we believe that this interaction might be crucial for protein specificity, because the alanine is not present in the PFLDH at this position. So this is an example where everything went well. We synthesized the nucleotide. It was accepted by polymerases. We could identify an aptamer that is highly specific. We could resolve the crystal structure. But unfortunately, this is not always the case. So we just like in the next couple of minutes, focus on a different project where we have started a few years ago now, and we tried to actually decorate aptamers with ruthenium complexes. This is with the idea of trying to improve the specificity of the photodynamic therapy, where actually photosensitizer are injected into patients and is shown onto these photosensitizers, essentially then produce ROS, which induce then cell death. But however, the problem with this treatment modality is that it does not have any specificity because the photosensitizers, ruthenium complexes or small molecules, do not have any specificity for healthy. I cannot distinguish cancer from healthy cells. So we wanted to synthesize modified nucleoside triphosphates that are equipped with various photosensitizers that are produced by my colleague Gilles Gasser at Chimie Paritech in Paris, and try to identify aptamers. So we've synthesized a large series of modified nucleoside triphosphates equipped with these polypyridyl equipped ruthenium complexes, which are a bit reminiscent of the complexes introduced by Andrew Kellett yesterday. Um, but unfortunately, these are not very compatible with aptamer selections, not really because they are not good substrates for polymerases, but because they intercalate into DNA even when connected to nucleotides and oligonucleotides. So we had to find ways around this problem. So one alternative was just to synthesize nucleoside triphosphates equipped with other photosensitizers, this time not metal complexes, but small derivatives, which are now, which resolves the issue of intercalation, and they're really all good substrates, and we are using these in aptamer selections. Another way around it is the post-Salex modification. So essentially, you can take an existing aptamer, in our case, the AS1411, which is one of the only aptamers that was not identified by Salex, which forms G quadruplexes and binds to nucleolin with very high affinity. So the idea here was to prove that actually aptamers can convey specificity in the treatment, while the PDT treatment, while waiting for a chemically modified aptamer obtained by Salex. So we use these ruthenium complexes, attach them by click chemistry, which was beautifully introduced yesterday by Andrew Kellett and Tom Brown, and could synthesize these modified aptamers and could show that, oh, sorry for it, this little modification here, but that actually they convey specificity to the PDT treatment. So let me now switch gears and go to the second and last part of this short presentation, where we try to develop de novo synthesis of chemically modified oligonucleotides. So as you all know, you can either produce antisense or short chemically modified oligonucleotides using phosphoramidite chemistry, which was introduced by Marvin Caruthers, which is a very good protocol, but is limited to oligos shorter than, say, about 130, 150 nucleotides. Alternatively, you can use, as I've just shown, polymerase-mediated incorporation of modified nucleotides, which works very well, which as exemplified, for instance, by the production of mRNA vaccines. But if you use that approach, all the nucleotides, so if you use a modified thymine, for instance, all the T's will be modified. So you can't have a mixture of modified and unmodified nucleotides here. So we tried to combine both approaches using solid phase synthesis and polymerase mediated synthesis. The idea is not novel and is shown here on this cartoon. So the idea is to use either template independent or template dependent DNA polymerases combined with temporarily blocked nucleotides, either at the level of the nucleobase or the sugar moiety. The polymerase will then incorporate one nucleotide, and the blocking group then prevents further additions of nucleotides, further insertions of nucleotides from occurring. After deblocking the temporary masking group, a new cycle can be produced. So this is an approach that works very well for DNA. Actually, there's a recent press release from this month from an American company where they could produce a DNA oligonucleotide of 1,000 nucleotides in length by this approach. However, very little research efforts have been dedicated to the synthesis of exonase and other chemically modified oligonucleotides. So when we started this project, we thought about like looking for blocking groups that would be not too bulky, but also that could be removed under mild conditions. So we first focus on phosphate groups because these can easily be removed by phosphatases, for instance, under very mild conditions. So we synthesized the DNA and LNA nucleotide triphosphates equipped with a 3' phosphate group and investigated their properties. Now, these nucleotides are not very good substrates for DNA polymerases, which is not particularly surprising due to the additional negative charges at the 3' end of the nucleotides, but this is not the major issue. Actually, in the course of these experiments, we could observe that actually DNA polymerases had a phosphatase activity because the phosphodiester linkages of both the DNA and the RNA nucleotide were cleaved, and hence there were multiple incorporation events, which is obviously not what we want. So we then went back to classical organic synthesis and focused on blocking groups that are traditionally used in nucleoside chemistry, and synthesized various DNA and LNA nucleotides. Then we converted these into the corresponding nucleoside triphosphates and investigated their properties. So to make a long story short, they're not very good substrates because we can have either just like singular incorporation events producing the N+1 product in moderate yields, or sometimes the esterase activity of polymerases removes the masking group of especially ester modified nucleotides, and you can have multiple incorporation. There's one notable example where this is not the case. It's with a polymerase called polyuridine polymerase, PUP, where actually we have clean and efficient production of the expected product. And so we're continuing to work on this to have more potent chemically modified nucleotide analogs. Right, so I hope I did not bore you too much, and I could show you what we tried to do with modified nucleoside triphosphates. Essentially, we tried to expand the chemistry that is available in SELEX to identify aptamers with enhanced properties, and we are building up on this controlled enzymatic synthesis of modified oligonucleotides. We now will have started a program where we try to introduce base modified nucleotides and RNA nucleotides by this approach, especially focusing on the PUP polymerase. I will thank all the people of my lab, because without all them, this work would obviously not be possible. I would like to thank especially Pascal Rotlisberger, who's done the cubomer selection and synthesis of the cubane modified nucleotides, Germain Niogre, PhD student, who's working on the ruthenium-based system, Nazaris Sabat, who's a postdoc, who works on the de novo synthesis of modified nucleotides. And I would like to thank all the financial support, and obviously you for your kind attention. Thank you very much.